Hello world, today we will learn about temporal difference or TD learning. TD learning, what is temporal difference learning? How we can define it? This is what we are going to see first. In order to understand the TD learning, it will help to discuss how exactly a brain would react to and try to solve the problem of learning from interaction. With proper understanding and betterment, we can develop intelligent machines that can interact with the world like the way we humans do. In order to accomplish this, the agents would need to learn from the kind of online streaming data that we learn from every day. In real life, it's far from an episodic task that we have seen in the old MDP method. And it requires its agents to understand or constantly make decisions all day and every day. We get no break with our interactions with the world, right? Remember the Monte Carlo learning? Monte Carlo learning needs the episodes to end so that the return could be calculated. The return is then used as an estimate for the action values. But we cannot expect the same thing to happen in the real world. So we will need to come up with something else if we want to deal with more realistic learning in real world setting. Let's see how we can do it. So the main idea is if an agent is driving a car, instead of waiting for an episode to end, it will be able to estimate the probability at every turn if it is likely to crash or not. It is really necessary to calculate this and amend its strategy to avoid the disaster. To emphasize this, let's see how Monte Carlo approach would have done this. EMC will need the car crash every time it wants to learn anything, and it is like too expensive and also quite dangerous, right? So let's see. Instead of waiting to update values when the interaction ends, we will need to make the agent amend its predictions at every step. And once that is done, we will be able to use it to solve both continuous and episodic tasks. It is widely used in the reinforcement learning and lies at the heart of many state-of-the-art algorithms that you see in the news these days. Many of you may have already heard about the famous Pavlov's experiment in the classical conditioning. Let's see more deep about this. Showing food to a dog elicits a response in form of salivation. If we show a aromatic food to dog, it will start to salivate. This association is called unconditioned response, and it is caused by an unconditioned stimulus. So here, the unconditioned stimulus is the food and unconditioned response is the salivation. Let's say we have a whistle which the dog have not heard about before. If there is a whistle sound, the dog will get alert to see what's happened, but there will not be any response from the dog unless it threatens the dog. Now, in the second phase, we are going to pair these two. Every time a whistle is sounded, we are going to show the dog the food, and the dog will start to salivate. So, we will teach the dog like this. We will condition the dog with the whistle sound every time it's going to have its food. So, after some time, whenever the conditioned stimulus, a whistle sound is heard, the dog will start to salivate, expecting for the food, even if the food is not there in real. This is called conditioned stimulus, and the salivation of the dog at this condition is called conditioned response. The term temporal difference was first used by Dr. Richard S. Sutton in 1988. The interesting thing about Dr. Sutton's research is that he motivated and explained TD from the point of view of an animal learning theory and showed that the TD model solves many problems with a simple time derivative approach. Let's see how he accomplished this. Dr. Sutton did a research on eye blink conditioning in rabbits. Here, a mild puff of air is directed to the rabbit's eyes. So whenever this happens, the rabbits will close its eyes. The unconditioned response in this case is closing the eyelid, whereas the conditioned stimulus is the air puff. During the conditioning, a red light is turned on before the air puff. The conditioning creates an association between the light and the eye blinks. There are two types of arrangements of stimuli in classical conditioning experiments. The first one is called the delay conditioning. The second one is trace conditioning. Let's see here. In the delay conditioning, the conditioned stimulus, the red light, extends throughout the unconditioned stimulus without any interval. But in the trace conditioning, there is a time interval called the trace interval between conditioned stimulus and the unconditioned stimulus. The delay between the conditioned and unconditioned stimulus is an important variable which is called interstimulus interval or ISI. Learning about the predictive relationships among stimuli is extremely important for surviving. This is the reason why it is widely present among all the species ranging from mice to humans. Learning means to accurately predicting the imminence weighted sum of future unconditioned stimulus of the intensity levels at each point of the time. In the eye blinking experiment, it has been observed that rabbits learn a weaker prediction for conditioned stimulus presented far in advance. Studying these results on eye blink conditioning, Dr. Sutton and Dr. Batto in 1990 found a correlation with the 3D framework. The reinforcement is weighted according to the imminence, that is the length of ISI. When slightly delayed, it carries a slightly less weight. When long delayed, it carries very little weight, and so on forth. This assumption is the core of 3D model of classical conditioning. The general rule behind TD applies to rabbits and to any artificial agents. New estimate is given by the sum of old estimate plus the step size of target minus old estimate, where target minus old estimate is an expression that defines the estimation of error or delta, which can be reduced moving off a step toward the real value, that is the target. The step size, sometimes called learning rate, is a parameter which determines to what extent the error has to be integrated in the new estimation. If the step size is 0, the agent does not learn anything at all. If the step size is 1, the agent considers only the most recent information. In some application, the step size changes at each time step. Processing the kth reward and the parameter is updated as 1 by k. But in real world condition, we normally keep it as 0.1. In the Monte Carlo method, to estimate the target, we take all the states visited into account until the end of the episode. So this is a flaw. Let's see why. In TD algorithm, we want to update the utility function after each visit. Because of this, we do not have all the states and we do not have all the values of the rewards. The only information that is available to us is the reward of t plus 1. The reward at t plus 1 and the utilities estimated before that. If we find a way to express the target using only those two values, we are done. To solve this issue, we can bootstrap, meaning that we can use the estimates to build new estimates. This is the most important part. If we group the discount rates, we obtain the equation. We got what we want. The target is now expressed by two quantities, the reward of t plus 1 and the updates rule of the state t plus 1, and both of them are known. Taking all these considerations into account, we can finally write the complete update rule. This update rule is fascinating. At the very first iteration, we are updating the utility table using trash. Initialized the utility values with random values or zeros, and what we are doing is taking one of these values at t plus 1 to update the state at t. How can the algorithm converge to real values? How can the algorithm converge to the real values? The magic happens when the agent meets a terminal state for the first time. The update rule found in the previous part is the simplest form of TD learning. It is called TD of 0. So this algorithm TD0 allows estimating the utility values following a specific policy. We are in the passive learning case for prediction, and we are in the model free reinforcement learning too, meaning that we do not have the transition model available. To estimate the utility function, we can only move in the world that we have visibility towards. Using again the cleaning robot example we saw in our previous episodes, I want to show you that what does it mean to apply the TD algorithm to a single episode. I'm going to use our old example of Roomba cleaning a grid world, where the robot starts at 1 1 and reaches the terminal state 4 by 3 after 7 steps. Applying the TD algorithm means to move step by step considering only the state at the t and the state at t plus 1. That is, after each step we get the utility value and the reward at t plus 1, and we update the value at t. The TD of 0 algorithm ignores the past states, and this is shown by the shadow I added to above states. Let us apply the temporal difference algorithm to our previous Roomba episodes with a discount rate of 0.9, which is the gamma value, and the learning rate of 0.1, which is the alpha value. The red frames that I have described in all these diagrams represents the utility value has been updated at each visit. Now let's apply the values to the algorithm. So the calculation for updating the utility at 1, 1 is V of S, that is 0.0, plus alpha, the learning rate of 0.1, then the reward minus 0.04 plus 0.9, which is the discount rate, and the utility value of the previous state 0.0 minus the value of current state 0.0, which gives the answer. Let's update this for all our episodes. Similarly, to 1, 1, the algorithm updates the state at 1, 2. At k equal to 3, the robot goes back and the calculation takes the form of 0.0 plus 0.1 minus 0.04 plus 0.9 of minus 0.04 minus 0.0, which gives us a value. We will apply the same to find the total utility matrix of our final state. So this is how we applied temporal difference learning to our Roomba problem. Now let's discuss how we can improve this. However, there is something that I did not talk about. What is the 0 contained in the name of the algorithm means? To understand what 0 means, I have to introduce the eligibility traces. Let's see. TD of 0 algorithm does not take past states into account. What matters in TD of 0 is the current state and the state at t plus 1. However, it would be useful to extend what learned at t plus 1 to the previous states. To achieve this objective, it is necessary to have a short-term memory mechanism to store the states which have been visited in the last steps. For each state S at time t, we can define the e base t of state as the eligibility trace. Here, the gamma is the discount rate and lambda belongs to the set of 0 to 1. And this is also called as decay parameter or trace decay or accumulating trace, which defines the update weight for each state visited. When 0 less than lambda or less than 1, the traces decreases in time. This allows giving a small weight to infrequent states. For lambda equals 0, we have the TD of 0 case, and only the immediately preceding prediction is updated. For lambda equal to 1, we have TD of 1, where all the preceding predictions are equally updated. Here, we can graphically represent TD of lambda with a non-uniform shadow which partially hides the old state and shows only the recent ones. Now, it's time to define the update rule for TD of lambda. With the help of estimation error that we defined earlier, we can update the utility function as follows. Okay, let me explain more. If we apply the same algorithm, the results of the update for TD of 0 and TD of lambda are the same along all the visits. but the last one. When the robot reaches the charging station, the reward of positive 1 is given. The update rule returns a positive value. In TD of 0, the result is propagated only to the previous state 3, 3. In TD of lambda, the result is propagated back to all the previous states thanks to the eligibility traces, right? The decay value of the traces gives more weight to the last states. As I told you, the utility traces mechanism helps to speed up the convergence. It is easy to understand why. If you consider that in our example, TD of 0 needs 5 episodes in order to reach the same results of TD of lambda. Let's do a Python implementation of TD of lambda. It is really straightforward. We only need to add eligibility matrix and the update rule. Here we define a function, update utility, that can take utility matrix, trace matrix, and alpha and delta. Let's see what are these things. Utility matrix is the matrix before the update, and alpha, we know it is the learning rate, and delta, the error estimation. The utility matrix is given by the alpha into delta into trace matrix. It's straightforward, right? The same for the eligibility, update eligibility. We give the trace matrix, gamma, and lambda function, and we get the result. The main loop is much simpler than the NC methods. In this case, we do not have any first visit constraints, and all we need to do is to apply the update rule. For every turn, we need to reset, take action, move one step, estimate the error delta, update the utility matrix, and update the trace matrix. Temporal difference is an important algorithm in the reinforcement learning space. Try to apply the TD learning to some of the OpenAI gym environments and share the results in the comment section. Thanks for watching this video. I hope you find it useful. Please share your feedback so I can apply reinforcement learning to make myself better.